locus, or locus, however you say the word. Basically, what is it? A collection of points whose location is determined by some stated law. What? That's just a real fancy way of saying, hey, it's a number plane graph. Because if you think about it, they're all got some stated law. Probably y equals x squared, a hyperbola, y equals 1 on x, and so on and so on. So they are all examples of loci. The difference, I guess, with this is we're used to seeing an algebraic description, as I say, y equals x squared and so on. But it could be a geometric description, such as this. Find the locus of the point, which is always 4 units from the origin. I guess there's 2 ways of solving it. One's just to think about the problem and imagine what's happening, and then you come up with, oh, what sort of shape would this be? There's an example of one. That would be 4 units away from the origin. Oh, so would that one. So would that one. Oh, and that one. Oh, and that one. Oh, that one would too. So would that one. Oh yeah, I think that one would. Oh, there's another one. Oh, and another. Oh, that one would. Oh, that one. And after a while, you get a feeling for what the shape is. Where? There it is. It's our circle. Radius 4, and if we remember our equation for that, it is, of course, x squared plus y squared equals 16. Now, if I didn't know that, if I couldn't imagine what it is, what I do is I'll just plot 1 and I'll give it a random coordinates xy. Okay, I don't know what the coordinates are, xy. But I can then go back to coordinate geometry formulas and say, well, what do I know about this random point? I know the distance from that point to the origin is 4. Okay, so the square root of x minus 0 squared plus y minus 0, well, that gets me x squared plus y squared is 16, which is the equation. So I guess the first idea is to, say, intuitively think about the problem. And if you're going, yeah, not quite sure, then we can always fall back to formulas. The point moves so that it's always 5 units away from the y-axis. Okay, there's my random point. It's always 5 units away from the y-axis. Now, you might have already worked out what it is, but we're saying that distance, because whenever we're talking about distance from a point to a line, perpendicular distance, so in this case it's a horizontal distance, that means the y value would be the same at the y-intercept, which we've called very creatively y, but it'll be 0y. So we're saying the distance is 5. So x squared is 25, and we get an answer you might not have expected when you first thought of it. Because actually there's 2 possibilities. I never said it was on the right-hand side of the y-axis. It could be on the left-hand side of the y-axis. So there's actually 2 possibilities here. It could be x equals plus or minus 5. A point moves so that it's always 3 units away from the line y equals x plus 1. Now, there's a very common mistake here when people intuitively think about it. They go, well, if I'm just adding 3, they come up with the answer y equals x plus 4. And that is incorrect. Because as I say, it's the perpendicular distance. There's y equals x plus 1. There's random point. We're saying that perpendicular distance is 3. You're doing pretty good if you can just intuitively go, oh, that would be this. A little bit of working involved here. I'm going to use the perpendicular distance formula. So random point is xy. So we get x minus y plus 1. So the general form of the line, absolute value of, over the square root of 1 squared plus negative 1 squared. That'll equal 3. So I've ended up with an absolute value equation to solve. So either x minus y plus 1 is 3 root 2, or the negative of x minus y plus 1 is 3 root 2. I'll put it in general form. So there's the equation of the line. Now if you just intuitively came up with that, well done. X minus y plus 1 minus 3 root 2 is equal to 0. The other one, well, let's play around with it. There we go. X minus y plus 1 plus 3 root 2, because again, I could be on either side of the line. A point moves so the distance from the x-axis is always 5 times as great 5 times as great. So there's random point. So if I go down to the x-axis, the x-intercept will be x0, go across to the y-axis. So the one to the x-axis is the bigger one. So I'll call it d and 5d if you like. All right. So this distance to the y-axis, so x minus x squared plus y minus 0 squared, is 5 times the distance to the x-axis. I guess the common mistake on this one is to have the 5 on the wrong side. Square both sides. Again, I get 2 possibilities. Y is plus or minus 5x. Because once again, it could have been over in the other quadrant. A point moves, this time from the point 1, 2 is the same as its distance from the point 5, negative 4. So there's 1, 2, there's 5, negative 4. Random point, well, I'll pick the midpoint because I know for sure in the middle that's going to be one possibility, but I've still given it random coordinates, x, y. So I know, yes, the midpoint will work. But what else? Well, the other thing I know is it must be the perpendicular bisector. That's easy enough to prove if you're unsure. Because if I was to pick another point, I could create congruent triangles. It would be side, angle, side. So it must be true anywhere on that perpendicular line. So all right, it's the perpendicular bisector of 1, 2 and 5, negative 4. So I can now go back to coordinate geometry. So the slope of the red line there, the blue line is minus 3 on 2. So the red line would be 2/3, the negative inverse. And the midpoint is 3, negative 1. We have a point, we have a slope. So we should be able to come up with an equation. There it is. 2x minus 3y minus 9 equals 0. Of course, another way I could have done this. I could have said the distance of that random point is equal. Because basically that was the definition of the locus. So I could just use the distance formulas. Square both sides. Whoa. But fortunately, look, we've got x squareds that'll cancel, y squareds that'll cancel. Bring it all to one side and hang on. Oh, of course, there's a common factor of 4 there that I can divide everything by and we get the same equation. Maybe that way is a little bit quicker. Who knows? But just as a little hint, that idea of perpendicular bisector comes in very handy later on in extension 2 when we're looking at complex numbers and locus. So exercise 9a.